Hello everyone and welcome back to the series of digital logic design, and today we will study about the storage elements. The storage elements used in the digital circuits can maintain a binary state indefinitely until directed by input signal to switch the states, and this binary information can be a 1 or 0. The major difference among various types of storage elements are in the number of inputs they possess and in the manner through which the inputs affect the binary state. The storage elements that operate with signal levels are referred as latches, and those controlled by clock transition are referred as flip-flop. All the memory elements which changes their output with the level of input signal are known as latches, and all the memory elements which changes their output through the clock transition are known as flip-flop. If you look at the figure, this represents a common clock signal, which is in actually a square wave. This can be broadly divided into two categories. First one is level and second one is edges. The levels of the clock signal can be a constant level of logic 0 or of logic 1, where the edges can be a rising edge and a falling edge. A rising edge is a duration in which the clock signal changes its level from 0 to 1, where a falling edge is a duration in which a clock signal changes its value from logic 1 to logic 0. So the latches are said to be level sensitive, while the flip-flops are edge sensitive devices. The storage elements used in the clock sequential circuits are flip-flop. A flip-flop is a binary storage device and is capable of storing one bit of information. So the output of flip-flop can be either a 0 or a 1. So a sequential circuit may use as many flip-flops to store as many bits as necessary, and the outputs or the values stored are formed by the combinational logic function of the inputs to the circuit or the values stored in the flip-flop, or both can be used. Similarly, the value stored in the flip-flop when the clock pulse occurs is also determined by the input to the circuit or the values presently stored in the flip-flop, or both. So we can say that a new value is stored when a pulse of clock signal occurs, or the value of a flip-flop is changed only with the occurrence of a clock signal. And before the clock pulse, the combinational logic forming the next value of the flip-flop must have reached a stable value, because after occurrence of clock signal, the same value present at the input of the flip-flop will be stored. So the block diagram of synchronous sequential circuit is shown here, which consists of combinational circuit, a flip-flop, and a series of clock pulses. Now we can say that the change in the state of the flip-flop is initiated by a clock pulse transition. For example, when a value of clock signal changes from 0 to 1 or from 1 to 0. When a clock pulse is not active, the feedback loop between the value stored in the flip-flop and the value formed at the input of the flip-flop is effectively broken, because the flip-flop output cannot change even if the outputs of the combinational circuit driving their inputs change in the value. Thus, the transition from one state to the next state occurs only at the predetermined intervals dedicated by the clock pulses. Now we will study about the latches, and we will start with SR latch. The SR latch is a circuit which consists of two cross-coupled NOR gates or two cross-coupled NAND gates. The SR latch has two inputs. First one is represented by S and is used for set, and second one is represented by R and is used for reset. The outputs of SR latch are represented by Q and Q prime, and these outputs are normally complement of each other. The SR latch constructed with two cross-coupled NOR gate is shown in the figure. The SR latch has two useful states. When output Q is equal to 1 and Q prime equals to 0, the latch is said to be in the set state. And similarly, when the Q is equal to 0 and Q prime is equal to 1, then the latch is said to be in the reset state. However, when both the inputs are equal to 1 at the same time, then with this condition, both outputs are equal to 0. And consequently, in practical application, setting both inputs equal to 1 is forbidden, because we have defined earlier that both the outputs will be complement of each other, where in this case, both the outputs are equal. So, setting both inputs equal to 1 is a forbidden state. Under normal condition, both inputs of the latch remains at 0 unless the state has to be changed. So the normal inputs will be 0, and whenever you have to set or reset the latch, you will apply input, and after then both inputs again will be returned to 0. The application of momentary 1 to the set input causes the latch to go to the set state. Like if you apply 1 to the set input and 0 to the reset input, we know that a NOR gate consists of OR gate followed by a NOT gate. So if single input of OR gate is 1, then its output is equal to 1, and followed by a complement, the output will be 0. So Q prime will have a value of 0. So this 0 will be transferred to the second input of the first latch, and we know that reset input is also 0. So 0 plus 0 will give us a 0, and with inverter it will be changed into 1. So Q will have a value of 1 and Q prime will have a value of 0. Now the latch is in the set state, so the S input must go back to 0 before any other changes take place in order to avoid the occurrence of undefined next state that results from the forbidden input condition. If you look at the function table, the two conditions causes the circuit to be in the set state. First one is set inputs equal to 1 and reset input is equal to 0. Once the latch is in the set state, you can change both the states to 0, then the latch will remain in the set state. Now once both the inputs are 0, so we can reset the SR latch by applying 1 at the reset input and 0 at the set input. When R is equal to 1 is applied, the output of OR gate will be 1, and after the inverter, the Q output will be equal to 0. Now the same 0 will be transferred to second cross-coupled NOR gate, and we know that the set input is also equal to 0. So 0 plus 0 will give us 0, and after inversion it will be 1. So Q will have a value of 0 and Q prime will have a value of 1. So through these steps our latch will be in the reset state. Once the reset state is achieved, the input applied at R can be removed, where after the removal the circuit will remain in the reset state. Thus both input S and R equal to 0, and the latch can be either in the set state or in the reset state, depending on which input was applied most recently. Now if 1 is applied to both the inputs S and R of the latch, both the output goes to the 0, because the circuit consists of two cross-coupled NOR gates, and a NOR gate is formed by OR gate followed by a NOT gate. So if one input of the OR gate is 1, then output is definitely 1, and 1 followed by a NOT gate will give a result of 0. So both the outputs will be 0. Now this action produces an undefined next state because the state that results from the input transition depend on the order in which they return to 0. And it also violates the requirement that output must be complement of each other. So in normal condition, this is avoided by making sure that ones are not applied to both inputs simultaneously.
Thanks for watching the video and stay connected for more interesting videos.